Now in this type of PN junction diode, we had this was P and this was N. P, N. Now forward bias was when the P was connected to the positive terminal and N was connected to the negative terminal. So this was my depletion layer, this, and this was my depletion layer. Now if I change the polarity, or if I connect the negative charge with P and the positive charge with N, then this type of connection is known as your PN junction diode in reverse bias. This connection is known as reverse bias. So now the question is, what exactly happens in reverse bias? Initially what we found was there is a formation of depletion layer. Now this is N type, this is P type. So all the excess electron comes over here and all the holes comes over here. Now if I take the negative charge, if I put over here a negative charge, so if I put a negative charge over here, then what I can see is, now this was neutral. Now there was this electrons over here, there was this electrons over here, and there were holes over here. It was equally distributed and it was in steady state. Now as soon as I put a negative charge over here, the holes will try to come over here. The holes, that is positive charge, will try to come over here, and as a result the electrons will be over here. There will be an accumulation of electrons over here. Similarly, if this is positive charge, then electrons will start to come over here and the holes will start to accumulate in this junction, that is in the PN junction. The depletion layer, if you look at the depletion layer, this is known as a depletion layer. Depletion layer will start to increase. And this what happens in your PN junction diode connected in reverse bias. So in a way, because of this logic, we see that there is an increase in depletion layer in this junction. Which will further stop the flow of carriers from over this point to this point, or this point to this point. So now what exactly happens is, say suppose this is your N. Now if a hole in your N, or if a electron in P, now if I draw this a bit more properly, this is a huge depletion layer. Now the electric field so formed in this particular arrangement is such that if this is N and this is P, so we know there are electrons and there are holes present, but in random motion, say suppose a hole comes over at this point, so it will be swept over to the other side. And similarly, if an electron is coming over here, it will be swept to the other side. So we can see that because of the random motion, now it does not matter upon your potential. This current that is produced because of the random motion, that is, when it comes close to this region, this particular hole gets, or say this particular electron gets swept to the other side, and this comes to the other side. This is known as drift current. And this drift current is not depending upon your potential that has been applied on this point. So now what you can see is the diode reverse current is not very much. The reverse current now you can see that the reverse current is not very much because it is stopping the flow. It is stopping the flow of further charges because the depletion layer a, is larger as compared to your forward bias. So this is stopping the flow of charges. So the diode reverse current is not very much dependent on the applied voltage. Now even if you apply voltage, you will see that there is not much flow of current. So even a small voltage is sufficient to sweep the minority carriers from one side of the junction to another. So because this part, this voltage is huge, so a small amount of voltage over here is sufficient to transform or to carry the minority charges, as we have discussed what is minority charges, from this particular point to this particular point. So it is very easy. So the current is not limited by the magnitude of the applied voltage. Now this is important. Current is not limited to the magnitude of applied voltage. So this is what happens in reverse bias. Now a special condition arises when the current under reverse bias is essentially voltage independent, that we know up to a critical bias voltage. So no matter if you increase the voltage, the current will not have that sufficient increase. But there is a condition. That condition is known as your breakdown voltage. Breakdown voltage. Now what happens in breakdown voltage is that after it reaches a breakdown voltage, it can overcome this barrier. It can overcome this barrier. As soon as it overcomes this particular barrier, the electrons and the holes start to recombine among each other. They will start to recombine. This is recombine. And when this recombination takes place, there is a sharp increase of current. We can say there is a sharp increase of current. Sharp increase of current. So this happens in reverse bias and this sharp increase of current. And because of this sharp increase of current, that is flow of charges, heat is generated. Heat is generated. And because of this generated heat, it can destroy the PN junction. So if you look in your market, the PN junction always has a breakdown voltage. This is a breakdown voltage which is given by the manufacturer. So this is what you can understand as the first introduction of PN junction diode under reverse bias. And let's have a look as to how can we use this particular reverse bias in our different electronic devices.